Okay, so what I want to do real quick is a follow-up to the previous video on Finite Automata, and this is going to be more narrowing in on the languages that they recognize, so we're going to talk about regular languages. So, let's go ahead and swap over to our slides, and again, just regular languages. Now, when dealing with Finite Automata, we often are attempting to ascertain what language it recognizes. So we want to see like what all types of strings does it accept, if it accepts any, and basically try to formulate some pattern and more quantify that down to an actual language. And any language that a finite automata can recognize is what we regard as a regular language. So while our previous finite automatas that we've gone over in the previous video, they were pretty simplistic, but we can essentially make them more complex, and we will definitely do that as we expand beyond the realm of finite automata. And the whole goal is to try to basically make more powerful machines and models and whatnot to expand the types of languages that we can characterize and types of grammars that we'll eventually get to as well. So, to essentially determine what languages can be accepted and recognized and whatnot, we have three conditions. That's going to be quantified on these three guys right here. So the first one, if you look down here, is the machine must have a start state. That is this bit right here. And then 2, the machine must go from state to state according to a transition function. We did that in the previous video by making transition tables, and those basically characterize how the navigation of the finite automata works. And then finally, we have the set of F, which is going to be our accept states. We have to actually have strings are accepted. Again, we can technically have a finite automata that recognizes the language of no strings, which is the empty language. That's kind of more of a exception to the rule here. So, to verify languages, let's take a look at a more complex state diagram. And that's this one you see over in the bottom right of Q1, Q0, Q1, Q2. And that is M5, and our alphabet is a bit more complex. Now we have 4, so we have this reset signal, 0, 1, and a 2. We'll consider reset as a single symbol. Again, this is just going to be one thing, not each character here. So we have 4 here. And we can see that we start with 0. It can accept an empty string. That's one thing to note. It loops on 0 and reset. On 1, it goes to Q1. On 2, it goes to Q2. And that's 1, 2, 3, 4. That's everything for Q0. And we move on to Q1. On reset, it goes back to Q0. On 0, it loops. On 1, it goes to Q2. And on 2, it goes back to Q0. That's all 4 of those. And on Q2 here, we have reset going back to Q0. 1 going back to Q0, 0 looping on itself, and 2 actually going back to Q1. So if we notice, 0 in all 3 states is a loop, doesn't change anything. Reset seems to always be going back to Q0, and we go to Q0 to 1 and 2 is basically counting up. And then 2 goes back here. Now, there's not a whole lot of rhyme or reason. Unless we actually know what we're looking at. So we can notice all of those, and then if we look at 1 and 2, it'll take a little bit more idea of what's going on than just being able to just look at this and say, oh, this is exactly what's happening. So moving on, goal of this finite automaton is to actually add up the numeric inputs and then accept if the sum of those inputs is divisible by 3. The reset signal is basically used to reset the sum. So if it's just starting to add up and get kind of messy, then we just reset and it completely clears out what we're looking at. So I'm gonna make a sum variable real quick. Right over here. So we have in 1 and 0. That'll be reset, but let's just take a look at this. So 1 plus 0 would be 1. Is that divisible by 3? Let's find out. 1 transfers, 0 does this, and we end in a non-accepting state, so no. At this point it wouldn't. If we reset, clear out sum, we're about to Q0. I mean, also this sum of 0 divisible by 3, so that is correct. Empty string would be okay, because 0 is divisible by 3 technically, or 3 is divisible by 0. It divides, it's fine. It's a little bit weird. 2, 2. How does that work? 2, 2. Oh, sum's 4. 4 divided by 3. That would be 1. 1/3. Essentially, it looks like this is doing modulus, essentially. 4 divided by 3 is a 1 remainder. And then we reset because obviously this doesn't accept. And we do 0, 1, 2, it'd be 0 plus 1 plus 2 would be 3. 3 is divisible. Let's check this. So 0 loop, 1 transition, and then 2 goes back to Q0. So yeah, it looks like this is actually just quantifying modulus 3 on the sum of the inputs with a reset signal, just to, I guess, make things a bit more interesting. So let's see what happens if we do a custom string real quick. Let's do 2, 1, 2, 1, 0, 0, 1, 2. Alright, I'm not gonna count that up. That's just random. Let's go. 2, 1, 2, 1, 0, 0, 1, 2. Well, that would accept. What does add up as? 2 plus 1 is 3, 5, 6, 6, 6, 7, 8, 9. Oh, yeah, this would be 9. And that is definitely divisible by 3. So, yeah, if we look at it, we also need to see, do we have all 3 things? So their string they did is 1, 0 reset, 2, 2 reset, 0, 1, 2. Verify that it meets all 3 requirements, because we can look at the actual transition sequence, which would be this cacophony right here. It's a lot of inputs, but those are all legal and valid transitions. We have a start state of Q0, and then we have these two, and we just have an accept state at Q0 as well. So all 3 of these are met, and we can actually characterize its language as all strings where the sum of the symbols in W is 0 modulo 3, except that reset resets the count to 0. Be kind of the idea of this. We can also do something like determining if things are even or odd. And yes, I know technically we would need a start state here, an accepting state, but this is looking at a general approach for even and odd counting. So we know that the empty string of epsilon should be in the even state. So we're just going to say our starting state is even because 0 is even. And that's where we're at right now. So depending on what we are counting, it looks like we're counting, 1 in this case. They're alphabet 0, 1, and then even odd. We don't have an accept state, but we could have an accept state of even or odd. This one's more open to interpretation, but you could probably just say, let's do this. Start Q even, and we'll accept if we have an odd. Wow, that was egregious. Wow. Okay, sure, that is the worst circle that's ever been drawn in the history of mankind, but there it is. So Q even, if we just say 1, 0, 1, 1, 0, 1, that's 1, 2, 3, 4, that should accept. Zeros are not going to affect the state because they don't add anything essentially. So we're starting at 0, we do 1, so an odd amount of 1s, now an even amount of 1s, odd amount of 1s, well, you know what, here, I'll do it. 1, 0, 1, 1, 0, 1. Oh, wrong accept. Now I'll accept. I thought it was kind of even, not odd about that. What we can say is 1, 2, 3, 4, 5. So we have 5 odds. We're counting 1 essentially. And that's perfectly fine. So that's one we can do for more complex structure, and then we can also use it to identify substrings in a finite automaton. So we want to look at, say, substring that contains 0, 0, 1. So our alphabet is 0, 1, and we currently here have states of Q, Q0, Q0, 0, and then Q0, 0, 1, and nothing beyond that. Okay. So let's see if we can make something that breaks this. So 1, 0, 1, 0, 1, 1. That does not contain this substring at all. 1, 0, 1, 0, 1, 1. We didn't even get to here, which is fine because it's counting up. We only got to a single 0 instance. If I change this to 0, this actually should accept because we can see it right there. Okay, so 1, 0, 0, 0, 1, 1. That's perfectly fine. Now we don't care what comes before or after or anything. That's where these loops are coming into play. So this 0, 1 loop going on right here. Any number of zeros here. We only care about counting this 0 and this 0 because we need these 2 zeros. And once we have those 2 zeros, then we can just count any number of zeros right here. Because once we have 2, we know that as long as we get a single 1, we should be fine. Because let's try this. You're not guaranteed to be okay once you get those 2 zeros, or any number of zeros actually in this state, because you have to get this 1 at least. So it is 0, 0, 0, 0, 0, 0. This isn't happening if I do anything beforehand. Let's do 1 there. There we go. So 1, 1, 1, 0, 1, 0, 1. Let's see, 1, 2, 3, 4, 5, 6 zeros. But we'll never be able to accept on this because we would need at least this or 1 somewhere in here. Actually, you know what? Let's do this. Let's put a 1 right there. So we get to this. Let's do it again. 1, 1, 1, 0, 1, 0, 1, 0, 0, 0, 1. And the moment we accept here, get to the accepting state, we found the substring, we don't care anymore. We determined that this sequence does exist inside the input string, and then we can just loop on any input of the alphabet because it doesn't change the fact that we found what we were looking for. Now, moving on, we have regular operations. In every form of mathematics, whether it be basic arithmetic, propositional logic, Boolean arithmetic, it doesn't matter. There's always going to be some various inputs and then different mathematical operations you can use to manipulate those inputs, combine them in different ways, add them up, etc., etc. And in regular languages, and all the logic for Finite Automata is no different. We have regular operations that are going to be absolutely critical when it comes to making more complex models. So as I said in the last video, everything we're doing here is DFAs. Once we move to non-determinism and NFAs, these operations are going to be very, very common. So let's go ahead and take a look at them. So we have three very important operations that you're going to see these a lot when we get to regular expressions. but we're going to see them here first. Move on to NFAs, deal with them. Build up to like expressions, deal with them, and they'll be in grammars as well. So these three are basically the cornerstone for a lot of the actual mathematical operations in theory computation. So union, concatenation, and star. So these first two should be familiar. Union should be familiar, just basic discrete mathematics, or if you've done anything with databases and whatnot. So it's just taking elements from both sets essentially. It's like an OR, I believe. But yeah, it's literally just an OR right there. Concatenation, or rather than intersection, but concatenation makes a lot more sense here. It's anding them together essentially. Not exactly. You can kind of say it's like implicit multiplication in a way, but essentially it's taking elements from A and then tacking on elements from B afterwards. Star is probably pretty new, and its existence as a unary operation that is any number of repeated patterns of that language essentially. And that could be zero, it could just be empty. So A star could just be no instances of A, 1 instance of A, 36 instances of A, 795 instances, doesn't matter. It's just any number of repetition. You can think of it as a loop. So union takes all strings in both A and B and combines them into a single set. Concatenation, cross product, taking each string in B and appending them to each string in A. And star is a unary operation that takes any number of any of the strings in either A or B and combines them. I need to go in and remove one of those. It's a double take. Alright, so this is a decent example of using some standard English words in conjunction with these operations. Our alphabet is just A through Z, no big deal. Our regular language of A contains the strings of good and bad, and regular language of B contains the words of boy and girl. So kind of think about, I say this to my dogs all the time, so it's kind of what goes through my mind. So if I do A union B, we get all those elements OR together. So one set becomes just good, bad, boy, and girl, all as individual elements. The moment I move to concatenation, though, is when things get a little bit more interesting. Since it's a cross product, we're going to do number of elements in A times number of elements in B should be the number of elements in this entire set. So that ends up being 4 here. And we get good boy, good girl, bad boy, and bad girl as all the possible combinations of concatenating those together. And then we have A star. And this is kind of the weird one, because it is just only focusing on A, so you have good or bad, and it's just any way you can combine these in any infinite amount of repetition. So we have epsilon here, which is assuming that we don't have any, so that would be like A0, no instances of it. Good or bad will be some form of A1, and then good would be some form of A2, good bad some form of A2, bad good some form of A2, and we can mix and match these as much as we want, because again it's just some number of occurrences in a repetition. We can define it however we want. A star is very, very flexible essentially. Now that is essentially everything we're going to cover on regular languages right now. Again, this is kind of a tip the iceberg aspect here, but we will expand upon this a bit further when we move on to NFAs and whatnot. Those regular operations, that's just an introductory. We will get into their actual applications in the next video when we start covering non-determinism. But For now, hope that was helpful. Hope you learned something. I'll see you next video.